This is my Engineering Physics 2 EO4 sequential logic design project. The main task was to make a circuit cycle through my student number. First, I converted my student number into binary. Next, I came up with a state transition table down here using the binary state transitions for the stable loop of my student number cycle, and also implementing the JK truth table and excitation table to find the JK flip-flop inputs. Now I used bits Q3, Q2, Q1, and Q0 as the main output bits. However, I needed another counter bit as there's a repeated 0 and a repeated 3 in my circuit. So the first instance of these repeated bits is a 1 and the second instance is a 0. I chose to use sum of products implementation to find the logic functions from the K-mapping. Using color-coded boxes for the K-mapping corresponding to the color-coded boxes up here was very convenient in quickly filling in the tables, as it was sort of repetitive. Here's a summary of all the logic expressions that I derived for my J and K inputs. And then down here, I first of all simplified the J3 input by factoring out a Q1. And I also had to invert all of the K inputs up here because on the actual JK flip-flops, they are not K inputs. So I had to invert them. And when I inverted this one, here's some calculations, I arrived at this final expression that I would use for my for the gate implementation, for the series of gates that I would have to use for each input. So from all this information, I can tell that I need 7 OR gates and 8 AND gates for my multisim and physical build implementations. So this is my multisim diagram. So I have my 5 JK flip-flops right here. This is JK3, JK2, JK1, JK0, and JK4. Then I have the gates in groups corresponding to the logic expression for the correct input. So this one I believe goes to JK2, and then this one will go to its corresponding input, etc., etc. I used an inverter to invert the clock signal just to make the output on the display cleaner. And then this is the decoder chip. I have the corresponding outputs going to the inputs on the display. And then I also use the logic analyzer to find the timing diagram from the output of the circuit. So here's the timing diagram that I derived from the circuit, and as we can see, it cycles through the correct loop of numbers. So then it was on to my physical build implementation, and I started the physical build by placing my flip-flops, my AND gates, my OR gates, and I used an inverter too, even though later I realized I didn't have to, just because I did a similar thing in the multisim where I inverted the clock signal for the display. Realized I didn't have to do that. But anyways, yeah, you can see my chips are laid down here, as well as the outputs from the decoder going to the corresponding inputs on the display. And I also have my clock input in the top right, which I was actually able to save from my H7 design project, or H7 project, so I didn't have to rebuild it. I then connected the clock signal to all of the necessary chips. And after that, I connected green jumper wires to the J and not K inputs. I used black, blue, and white jumper wires for the gate networks. And this is my final circuit. So in the end, the output of my physical build was almost exact, except there was a weird issue with a 4 being outputted where the repeated 0 should have been. I was really confused by this because it was such a subtle difference, and I didn't know what could be wrong with the circuit to cause such a subtle difference but not affect anything else. So that was kind of strange, but I've elaborated on what I believe might be the cause in the reflection. Yeah, but overall, I enjoyed this design project, and I can see how similar concepts could be applied in things like microwave or oven clocks, or really any kind of clock or timer. So yeah, it's a powerful tool to design your own systems which provide a certain output given the previous state in a stable loop. So yeah, that's sequential logic design.